Hi, and welcome to Allen High School's discussion of chemistry at the APIB HL1 level. Kiddos, we are actually moving into one of the most, if not the most important section that we're going to cover. The ramifications, the applications of this material are far-reaching. They'll help you understand your biology classes more effectively. If you go to med school, if you go into medicines, these are really foundational principles that undergird a lot of the application of chemistry. Not only that, they are now a critical component of the AP curriculum. So let's have at it and see where we're going to be heading with this. Now, in the last unit, we talked about the bonding possibilities and bonding structures. And the ones that we concentrated on were network covalent, that long-range structure, ongoing repetition of covalent bonds. Metallic bonds, do you remember, and this is critical, that sea of electrons. That sea of electron model is going to have a lot of explanatory power for us. So we want to make sure that you can explain it, draw it, understand it, and apply it. We're going to look at ionic, and then we're going to look at what I call discrete covalent. Often they're called molecular. The terminology of this is a little bit confusing. So the key is to memorize some of the key network covalents that are going to pop up in the conversation. Now, let's start with this. Everything in chemistry is about attractive and repulsive forces. Everything. And so coming back to this, we used this formula when we talked about lattice energy. When we have two charges, the potential energy between those charges is given by this formula. And we're going to be using this again in a qualitative sense. If we increase the charge or magnitude, so that's our top, if we increase our numerator there, and what that's going to do is cause an increase in potential energy, assuming, and I'm talking about the magnitude of the potential energy. If it's an attractive force, the increase is going to make it more negative or more stable. Remember, negative was stable when we were talking about bonding. So I'm talking about really the absolute value in this conversation, all right? If it's a repulsive force, it's going to make it very, very positive, and that is not favorable. If we want to be looking at decreasing the distance between charges, and what we'll end up doing is we'll see an increase in attraction when that occurs. Not only that, we're going to see an increase in the energy required to break, whatever attraction that is. So let's look at our intermolecular forces. If you don't understand this part of the conversation, and I have what I think is a good learning opportunity for helping you to apply these more effectively. But if you don't understand these, you really need to get into See Me ASAP. Now, the one that all substances have in common is London dispersion forces. All right. Now, in books, you may see van der Waals forces when discussing intermolecular, but van der Waals is not always used consistently, so I'm going to avoid using it at all. And we will talk about the three, the London dispersion, dipole-dipole, and hydrogen bonding that we saw in pre-AP that we're going to unwrap to a much deeper level. The key to the London dispersion force is that it is a temporary or instantaneous shift in electron density. Every substance has an electron density. Hence, every substance experiences London dispersion to some degree. Now, if these are small, okay, then the London dispersion is going to tend to be very weak. But if we're dealing with very large, much bigger molecules, especially molecules that have a lot of contact area, then we have a significant electron density. And as you increase the electron density, Now, don't go by molar mass. This is not an issue of molar mass. Molar mass is calculated based on protons and neutrons. Now, you can use the molar mass to kind of get an estimate of the size of a molecule, but don't use it in this conversation. You want to be talking about the electron density. If you increase the electron density, you increase the polarizability of a molecule. Now, the polarizability is the ability to shift the electron density. Okay, that ability to shift the electron density, and I'll do a little demo of that, a little personal demo of that when we get into class. Large molecules with a lot of electron density have a high polarizability. We can shift that electron density, and that's what this picture is showing. Even helium, and it's tiny, really, really tiny, very, very weak force, but even helium has this ability. So if you have helium, helium's an atom. There's no preference one side or the other for electrons, but all it takes is one molecule to shift its electron density. And what that does is it induces the molecule next to it to shift its density, right? Because here's a little positive there, so the electrons are going to be attracted to that. And it's sort of like doing a wave when you're at an athletic event, like a ball game or something like that. So all it takes is one person to stand up, and then that causes the next person to stand up, and so forth. But the first one to stand up sits down. It's a temporary effect, right, when somebody does the wave. And that's what this is. It shifts temporarily. It induces. So one just randomly shifts. It induces or causes the next one to randomly shift, and then they go back to the way they were. And then the cycle starts over again. All right? Now, this shows hydrogen, and showing how hydrogen can do the same thing. Again, no polarization, no shift one direction or another. All it takes is one molecule to do a random shift in electrons. No cause, no seeming reason, it just shifts. You know, those electrons are just playing around in their molecular orbitals and they shift over. Well, that induces the next molecule, just like in the wave. Who causes that first person to jump up? It's just this random person who decides to start a wave. And that induces the person, hopefully, or the guy's going to feel like an idiot, induces the next person to shift or to stand up as well. Now, these partial positives and partial negatives are then attracted to one another. Okay? Now, London dispersion can be very, very weak, or those partial positive, partial negatives can be really strong. So don't assume just because it's only London dispersion available to a molecule that it's necessarily going to be weak. All right? Now, all substances have London dispersion, but this is the only intermolecular force between molecules for non-polar molecules. So if a discrete, we're talking with intermolecular, we're talking about those discrete covalent moleculars. Okay, and if they're non-polar, this is the only intermolecular force that can hold them together. Okay, and it can get large. If you increase that density, you increase the polarizability, you increase the partial positive. Remember, you start to make a figure 8 and end, and the partial negative, and you increase the strength of the London dispersion force. This is a critical statement here. You want to memorize that statement. We should make up a song, and then we should make a video of our song and post the video of our little London dispersion song. Okay, I know that was a lot on London dispersion, but they're very, very important. So I'm going to end the video for now. So until we're back again with dipole, dipole, this is, of course, signing off.